This shattering block represents the primary failure point of traditional graph databases in procurement analytics. When a system attempts to simultaneously query rigid relational data, fuzzy semantic clusters, and high-volume text at a billion-row scale, a monolithic architecture breaks. It cannot handle the conflicting performance demands of these three data types at once. To resolve this, the FPDS platform rejects the standalone graph database model. Instead, it builds three distinct interlocking graph structures natively inside Postgres. These layers each handle a specific slice of reality. The relational graph captures structural truth. The topic graph maps semantic meaning. The keyword graph tracks lexical presence of terms across the entire procurement corpus. These structures are designed to be mathematically fused at query time, serving as the grounding mechanism for large language model retrieval. By separating these three data dimensions natively within Postgres, the system bypasses standard query bottlenecks, creating a multi-dimensional data structure for retrieval. The first layer of this architecture relies on standard Postgres relational tables. Rather than using a separate graph database, the edges are formed entirely through native foreign key joins. A formal ontology is applied over this raw data. It utilizes a framework that categorizes every entity as either a continuant, a persistent object like a vendor or agency, or an occurrent, an event, such as a contract award or a solicitation. This two-tiered model separates schema from data. The top T-box tier establishes the theoretical framework. The bottom A-box tier contains data instances mapping upwards. This ontology defines 36 distinct object types, connected by 28 link types, categorized by functions like execution, evidence, and competition. Security and speed are managed at the database level. Row-level security spans 92 underlying tables, which feed 14 dedicated graph edge materialized views on a zero-downtime double buffer refresh cycle. This relational graph acts as the structural skeleton of the platform. Because analytical claims are versioned and tied directly to these records, the system maintains a permanent audit trail for every finding. With the structural skeleton established, the architecture introduces a second layer to manage the fuzzy semantic meaning within the text. This requires a topic generation pipeline run across every distinct corpus. The system utilizes BER topic for dimensionality reduction, clusters the results using HDBS scan, and extracts terms using class-based TF-IDF scoring. The volume of this semantic mapping is extensive. 588 active topic models manage nearly 55,000 unique topics, applied across 190 million assignments. Look at this vector map. These separated clouds highlight a specific engineering hurdle. Because these models are trained locally on specific datasets, they create isolated semantic silos. A topic discovered in SAM.gov opportunities has no inherent mathematical connection to a topic found in Prime Awards. Generating local semantic clusters is computationally straightforward. However, for system-wide retrieval, these clusters must be forced to speak the same mathematical language. The system solves these semantic silos through the canonical alignment layer. This is a centralized baseline of 2012 primary topics, trained via global centroid clustering across a multi-corpus sample. This vertical spine is the canonical baseline. Embedding models calculate similarity, allowing isolated datasets to cosine link to specific points. These connections use a six-signal ensemble filter, calculating strength with cosine similarity, Jacquard index, and combined weights for NAICS, keywords, temporal data, and agency alignment. A local topic only receives canonical status if it passes a promotion gate. This requires stable Leiden community detection, an alignment score of 0.70 or higher, and corroborating human expert review. These rigorous mathematical thresholds transform localized semantic noise into a single queryable intelligence layer spanning the entire platform. The next challenge is the structural fusion of the rigid relational database and the unified semantic graph. This diagram shows the intersection point. A rigid ontology node on the left and a semantic node on the right merge into a hybrid entity, the procurement area. A market area is defined as the mathematical intersection of a scope and a canonical theme. This interlock transforms the market area into a first-class mathematical object, integrated directly into the relational database structure. The final layer of the architecture focuses on the lexical presence of specific terms across the entire corpus. This uses a specialized extraction pipeline. A single-pass Aho-Korosik automaton scans text against a 1.19 million-term lexicon, supported by neural extraction from Keybert and Spacey. The resulting edge table contains 1.86 billion rows, making it the largest single graph structure in the platform. The scale of this data is managed through structural polymorphism. Instead of using separate join tables for every record type, a single row format references keywords against disparate parent types, such as contracts, grants, and documents. This architecture prevents the database schema from expanding with every new record type. It allows a single keyword query to traverse the entire procurement lifecycle through a single edge table. During query execution, these three graphs are mathematically fused into the platform's retrieval architecture, BERT Graph RAG. When queried, the system pulls structural facts, semantic alignments, and lexical matches into a central block. Surfaces are combined via reciprocal rank fusion at k equals 60 into a ranked list. Finally, a linear decay formula reorders the results, prioritizing recent activity. This temporal weighting ensures that LLM answers remain grounded in current operational reality, rather than surfacing stale historical data. This tripartite foundation also provides the training data for relational graph neural networks. These models train on the structural graph, using the semantic and lexical layers as node and edge features. By addressing relational integrity, semantic alignment, and lexical polymorphism at the Postgres level, the platform establishes a structured environment for AI to retrieve and reason over billion-row datasets.